great pleasure to do these introductions for our faculty seminars, and today is a particular pleasure for me. But I have to start by apologizing because I have to leave immediately after this introduction. So I apologize to François in front of all of you. My department, I have a home department, and we have a faculty meeting, and we're talking about important things, and I need to be there. So sorry about that. In any event, I'll try to keep this introduction relatively short. François, as most of you know, is the Albert G. Blanke Professor of Geosciences here at Princeton. He came to Princeton in 1994. Prior to that, he was a faculty member at MIT in the civil engineering department, in fact in Building 48, good old days in Building 48. And while he was there, he served for some time as director of the Parsons Lab. Parsons Lab is basically the department of civil engineering department. He has done many great things in regard to research and in regard to writing. He has a classic textbook that's used widely. For his research, he works broadly in the area of the interaction between trace metals and microorganisms, and has done remarkable work for which he has received many awards. He's a member of the National Academy of Sciences. He has a Distinguished Alumnus Award from Caltech, where he did his PhD, and many other kinds of awards. But I don't really want to focus on that. I want to end the introduction with a few comments about the fact that he has also served, as many of you know, as director of the Princeton Environmental Institute, PEI. He's done that for 3 terms, 2 of them consecutively from 1998 to 2006, and then he was called back into service from 2014 to 2017 as my immediate predecessor. And many of you will know that he has done many things to benefit PEI. Many of our faculty who are currently in PEI were hired by François. He initiated this faculty seminar series, which he likes to describe correctly as being unique on the campus, in that we get to hear from our colleagues from here at Princeton instead of outside speakers. He's done many other things. And I'll just mention one of my own experience with François, and then I'll give him the microphone. And that is that in his first term as director, he convinced me to be director of the Environmental Studies program, which is the undergraduate education part of PEI. And for me, it was a terrific experience. But I'll just tell you one of many things that François has done that no one here knows about, I'm sure. And that is that back in '98, the enrollment in our introductory course, ENV 201, had crashed, almost to single digits. And of course, I come in being completely naive about things. I said, I'll teach the course, that's okay. I'll pick up the course. Of course, I don't do a very good job in it. And François eventually decides the thing we need to do is to add a lab component to ENV 201. I say, okay, but I can't do that. I'm not a lab guy. I have other things to do. So we try to find someone to do it. And at the end of the day, we don't actually find anyone who's suitable. So François, as director of the program, simply decides that he will put the labs in place, and he will run the lab sections. And there are very few faculty, I would submit, who are willing to take that on with no reward whatsoever, other than knowing that he has a responsibility, at least in his own mind, to make sure that his institute and his program is done the way he wants it to be done. And that's one of many things that have impressed me very much about François in regard to his contributions to science, and in this case, his contribution to this institute, the Princeton Environmental Institute, that sponsors the seminar series. And so I will ask you, with your applause, to welcome François to give his talk, and also to thank him for his terrific years of service to the Princeton Environmental Institute.
That's hard to follow. You seem a little thing on my head.
I didn't tell a good story.
Oh, that's good. All right. So I've given many talks to colleagues and students in my very long career. Can you hear me? Are you okay with that? All right. But today is a bit different for me because my 2 young sons have decided to attend as well. And that's making it much more intimidating. This being a may I'll try. I have an accent, you have noticed, and also tend to speak quite fast. So feel free to ask questions, interrupt. It's all very much welcome. Michael didn't stop me on time. As soon as this is
in French, then you won't have an accent.
He's a friend of mine, by the way. All right, let's try this. So, a few years back, newspapers were pretty big headlines on ocean acidification. We discovered the idea that somehow CO2 in the atmosphere would go into the ocean. Interesting idea. And if you look at the scientific literature of the New York Times, here is a number of publications that I found on the Web of Science by plugging in CO2 in the atmosphere and ocean acidification. And you see that after a time with very few, this very few publications until about 2007, it's taken up, and now it's, well, this year it's going to be 1,000 publications. And I've read every single one of them. You see the problem, right? It's a subject which is immense. Some very good papers, some very bad papers, and a lot of them. All right, so here's my talk. I'm going to talk first about the chemistry, CO2 going into the surface ocean, acidifying the ocean. Then I'll talk about the effect on phytoplankton, and I spend much of my time on that, and that's because I know something about it, which is a very good reason. And the second reason it will not be as good is because I think that major effects on oceans will have to come through the effects on the beginning of the food chain, on the plants essentially. I think the rest is not so important. As long as you fix enough carbon, I think the oceans will be fine. Then I'll talk particularly about the problem of calcium carbonate precipitation, which is a lot of people excited. If you eat oysters or if you like corals, it's one of the big problems, possible problems. And then there's a whole very large section on indirect effects. And we prepared some slides, and I cut them off, because I thought you'd be tired by then. So, all right. So let's start with the atmospheric CO2 and ocean acidification. So here is a curve, which is well known, of CO2 in the past. We're going from 400,000 years ago, if I can get my pointer here, to the present. And you see up and down according to ice ages here, and of course the interglacial time. Now, there's a beautiful records that came from ice, and what's interesting here is that you can follow it up with actual measurements at Monadnois of CO2 in the atmosphere. And so you have a record which is now continuous essentially, starting 400, in fact now 850,000 years ago. The record was like almost a million years. And now we have a record. I first put the actual line there, it was a mess, because I've done a tiny bit of a mess of the whole thing. So I just printed a line out of nothing. And then here's what happens in the future. I have to put everything down because the scale is going to change. So the same data as before, and now it's printed down. The increase that we know of, and that's the future. And we don't know, of course, depends on that you're going to drive your car and other things like that. But it's going to be higher than today. We know it's going to be what, how far up, I don't know. 800 is a large value compared to previous field, which is 280 or so. So it's a large increase in CO2 in the atmosphere. Where does CO2 go? It's an old slide, I'm not sure the numbers are right, but it doesn't matter. Some of it, of course, comes from burning, some of it comes from deforestation. It goes partly in the atmosphere, partly taken up by the biota, and part goes into the ocean. About a quarter or a third goes into the ocean. And in the ocean, what happens? Well, it dissolves in the ocean. It's at equilibrium, more or less, in the atmosphere and ocean. And there it's used up by plants, which are eaten up by animals, so it disappears down. So it mixes down. But basically, at the top, you have the CO2 being used up by phytoplankton, and phytoplankton being eaten up, and the whole thing is exported. All right, so the data looks like this. This is data from the station Mauna Loa for the CO2 in the atmosphere. You see the up and down seasonally. Then a station Aloha, which is a little bit north of Manaloa. I can tell you what Aloha stands for, but it's full of bad jokes in general. All those names are full of jokes that are terrible. So tell them. A station Aloha, you have measurements of the surface CO2 in seawater. And what you see that it follows exactly what's in the atmosphere. It is below, and it has much more noise, right? It goes up and down much more. It has to do with the fact that things actually take up the CO2 to make plant mass, and they respire it, so there's a large amplitude, and it stays below because it doesn't have equilibrium in real time. Okay? So, where is that CO2? Here is a diagram which is a little old, it's 2004, but it's all right. This is how much of anthropogenic CO2 is in the ocean in micromolar. It's the total amount. It goes to about 40 at the surface here, and it gets less at depth. This is only the human anthropogenic value, right? And you see the North Atlantic, by the way, this is the profile here, going from here to there, from the south to the north. And in the north, of course, there is a downwelling of water, and so the CO2 penetrates deeper in the water, simply because of the physics of the ocean. The chemistry. So when I prepared the talk, I said, oh my God, people hate chemistry. And most people, except chemists, of course, hate chemistry. So how much chemistry can I put on the slides? And Satish will tell me, but I put as little as I could. Okay? And it's in big letters, so in principle, everybody should be happy. Right? Speaking to the ecologist right now. All right. So, here we have CO2, carbon dioxide, dissolving in water by breaking bicarbonate, and we receive a hydrogen ion. What happens to that? So CO2 up, if that hydrogen ion increases, okay, both of them increases, which means that we have more hydrogen ion. And I've put a scale down there so you can see this. I'm sorry. I'm going to have trouble here. So you see that typically we have now a pH of seawater which is 8.2 roughly on surface. It's the pH scale, which is really annoying because as there is more hydrogen ions, there is a lower number, and a higher number when there is more. Typical values right now are 8.2 or so. And if I now push this, it's going to be down at some point in the next century or so, around 8.5 down. So that's what we expect, simply from CO2 dissolving in the water and dissociating. Now, same graph as before, but I've put on it now the measurements of the pH, which is here, the green line. Again, it's noisy for the same reason that CO2 is emitting, it's a result of that. And this is the pH, which goes from, in this case, what, 812 to 807, right, something like that. 0.05 units or something of that sort. All right, so time series monitoring station. People have started deciding that we need to know what's happening and to start getting data that are essentially in a few weeks and do it for years and years, which was a success, by the way, of the Mauna Loa data in CO2, which is extraordinarily important to science because we got these measurements all the time over many years and we could see the increase. So people have decided to try to do that for acidification of the ocean. So the station I've mentioned already near Hawaii. There is one there at the Bermuda station, and there is one over there near the Canary Island. And there are others, but those are the principal ones. You can see the dates when they started. We're no longer in 2009, but the places haven't changed. All right. So here's the data for Aloha, Estok, and Bass. And you can see a decrease in pH, starting maybe on, consider the Bass line at something like 813 or something like that, and now probably 810 or so. So we can measure the decrease despite enormous noise, right? And there's enormous data, but we take enough data at the wrong enough time. And of course, it's not really noise, it has to do with biological activity. Now, I'm going back to the long-term scale. So I'm going back to 1,000 years before present. You've seen those data in less crunched form before. This is the interglacial and glacial, interglacial, glacial for the last 400,000 years. And there is a recent uptake, which is what we've been doing. And I'm giving you at the same time a value of the surface, the ocean pH. I won't explain to you how it's been done, but basically you can see the ocean pH essentially a symmetry to the CO2 in the atmosphere. And what's interesting here is what we think is going to happen, and that between now and the end of the century, we're going to be likely somewhere around here for CO2 and somewhere down here for the surface pH. So it's a dramatic change. The point I'm making is that those variations happen over millennia, and we're talking of something which is essentially instantaneous, which is the drop in pH, same way as the CO2 increase in the atmosphere. All right, so the chemistry is here. Where does CO2 go? CO2 gas dissolves in water, and that's about 7% of the CO2 gets into seawater, gets there, and most of it reacts with the carbonate ion to form bicarbonate. Carbonate ion is the main base in seawater. CO2 is the main acid. They're going to neutralize each other. And so you have a reaction in which CO2 reacts with carbonate to make bicarbonate. Bicarbonate is the main form of inorganic carbon in the ocean. Right? That's almost all of it. And so the main reaction is here. 93%, we can change the numbers a bit, but a very large fraction of it is not staying as CO2. It's reacting with the carbonate ion. Ocean acidification. I just lost my glasses. Speaking along with them. Okay. If we multiply CO2 in the water and gas by a factor of 2, we're going to multiply roughly the H plus concentration by a factor of 2, which means a decrease in the pH by 0.3 units. So that's something we expect to happen within the next 50 years, 100 years. It's time scale which is relevant to us or our children. Okay, that's the point. All right, so that was the chemistry. So what? Who cares, right? You probably won't be affected by the change of pH in the ocean when you go swimming. That's not an issue. Right? You shouldn't be worried about that. So the interesting part of this is not so much the chemistry per se, but the effect on the inhabitants of the ocean, which means the biota. So I'm going to talk about biological effects and looking at the same time the increase in CO2 and the decrease in pH. Why? Because they're completely linked to each other within a matter of seconds. So things are equilibrated, right? And so there is, in fact, ocean acidification is both the increase in CO2 and the decrease in pH, right? The two are simultaneous. And I'll introduce some phytoplankton species. Much of my work and which I will talk about today has to do with phytoplankton. These are diatoms. You've heard of those. They're very pretty, and they have a silica frustule. The hard part is silica. Those are coccolithophorids. They're a little bit smaller, and around them are calcium carbonate plates, okay, which can be shed off and come back on it. But they're armored with calcium carbonate. And here is a flagellate, and those do not have hard parts. They have a thick cell wall, but they are not armored with inorganic plates. What else about phytoplankton? Oh, one thing I wanted to say. So one thing about the plants, which are the plants of the ocean, they're very much unlike plants on land. My colleagues from EB are used to things that grow, and a tree takes a long time to become another tree, and then the grass takes days to grow. Those things here tend to reproduce almost every day or every other day, right? And they're eaten every day or every other day. We're thinking of something which is extremely rapidly growing, extremely rapidly being eaten. So it's a completely different ecosystem from that of man. So my EEB friends here will be confused because nothing happens the same way. All right, so I'm going to talk a bit more about acidification. I've told you that CO2 is going to go up, and H plus is going to go up as well, which the pH is going down. And without doing any experiment, you can think of what is likely to happen to those single-cell plants of the ocean, right? what's going to happen to them? Well, the CO2 up is sort of an advantage. What they're going to do, and I'll show you more, they're going to use the CO2 to make biomass. So that's a good thing for them. The pH going up, as I'll show you, is a problem because you have to control the inside pH. The pH of your blood is roughly 7.4. Inside those organisms, not very different, 7 something, right? Not exactly known depending on the organism, but it is controlled very carefully. If you change the pH of the ocean, you're going to have a problem of what you're going to do with the internal pH. How do you control it, right? So let's talk about the pH first. The interesting paradox is the following. There is more H plus inside than outside. So there's a tendency for H plus in terms of concentration to go outside, right, by diffusion. But it turns out that phytoplankton, like most cells, have a negative electrical potential inside compared to the outside. And the potential is sufficiently negative, minus 80 millivolts, for example, larger than 60 millivolts, which means that the tendency then is not to go outward, but to go inward, because the H plus is charged. If the potential is more negative inside, there's a tendency to go inside. And so despite the gradient of concentration which tends to push outside, in fact, the leakage of H plus is toward the inside of the cell, which means that you have to export the H plus. So there is a proton pump, H plus pump, that has to be activated and spend ATP and spend energy to make that happen. Right? That's true of most cells. Now let's talk about why CO2 should matter. And we have to talk about photosynthesis a little bit. So here is the sun, water. The light reaction consists in taking water and splitting it to make oxygen, right? That's what the light reaction does. And in so doing, you release electrons, okay, which then go into the dark reaction, where the electrons are going to reduce carbon dioxide to make organic matter. So the light reaction, the dark reaction. And the dark reaction is of great interest to us because the key enzyme in there is called rubisco. Ribulose, bisphosphate, carboxylase, oxygenase. Big name. It's also a very large enzyme. It's more than 400,000 daltons. So it's a very, very large molecule. And it happens to be the one responsible for actually reacting with carbon dioxide. It does react with carbon dioxide itself. So rubisco is not only large, I've told you about 500 kilodalton. It's also ancient. Must have existed more than 3 million years ago already. And it's very slow. Most enzymes we tend to think of as turning over in a matter of microseconds, nanoseconds sometimes. This is seconds, right? It takes seconds for rubisco to do its job, which means it's huge, it's slow, you need a lot of it. Okay? Here is the active center of rubisco. So this is the ribose bisphosphate. Phosphates are yellow, so you can see them. All right? And that's where CO2 is going to react. It has an affinity for CO2 which is very poor. Compared to the concentration in the atmosphere, rubisco is very, very bad. And the reason for that is because it evolved millions of years ago when CO2 in the atmosphere was much, much higher. So that enzyme is very ancient, was designed to work with large CO2 concentration, and now is not really adapted for the modern ocean. Concentration that it needs is much, much larger than that of seawater. So phytoplankton have to take CO2 from the outside and pump it inside and concentrate it so the enzyme can work. Because if you don't saturate the enzyme, you need more enzyme, and since it's a very large enzyme, it becomes extremely costly. Right? So it's an enzyme which is large enough that you want to nearly saturate it all the time, to be always working with CO2 pressure. So, what do we expect here? We expect that CO2 is a good thing because it's going to simplify phytoplankton getting CO2 and fixing it with rubisco. And the pH, the H plus going up is probably bad because it means that we have to export more H plus, right? So the expectations, we have not done any experiment, we've not any data, we expect roughly high CO2 to be good, low pH, highly stressed to be mapped. No experiment, no information. And the question, of course, is it possible that those two things are more or less cancel each other, which is one of the big issues. All right, so first after I talk about some experiments of a young lady who was here as a graduate student, now a postdoc still at Washington, Joanna Goldman, who worked with Michael Bender and me, and I'll show you very few data from her, but basically she did something interesting. Since she worked with Michael, she used 018, of course. Worked with Michael, of course, she used 018, and as a tracer. And basically, you can follow a number of reactions, but one thing of interest is to follow the fixation by Ruby's chloride with making 018 or 16, which you can measure with mass specs. And so you look at the reactions, and you can measure photosynthesis, growth and net, and all kinds of things. And I'll show very few data. And here is one set of data, which is gross photosynthesis, moles of oxygen per chlorophyll per day, as a function of light intensity, microeinstein per meter squared per second, and under different conditions of carbon dioxide and pH, 1381, 1378, 2681. We vary the two independently by playing with the chemistry of the system. And this is the organism we use, and what you see is nothing, the first approximation. Within the noise of the data, this organism is indifferent over the range of experimental conditions to the changes in pH and in carbon dioxide concentration. That's rather interesting. Not much. All right. I'm going to show you other data for other organisms from other authors. And I don't want to show you all those curves all the time. It takes forever and a mess. So I'm going to simplify the presentation by telling you only about two parameters. One is the slope of this curve at the origin, called alpha, and then the Pmax, which is the maximum rate obtained at high light. Right? So at low light, there is an increase, which is linear with light. At high light, it becomes saturated. Two parameters essentially define the response of any organism. All right, so it's a bunch of data, not that many data. It's in a review by Kate McKay. And what you see is all the data that she could find, and it's 8 for coprolithophore plus 12 for diatoms. Now, there happen that many studies that looked at the response as a function of light. At the time, other large phytoplankton and lysotroph, which are cyanobacteria. And so the same thing here. So this is the alpha, this is the slope, and this is the maximum, the Pmax. All of that is normalized to the value at 380 ppm CO2, and the variations are between 650 and 1,000 ppm with all the data together. So what you see is not enormous effect. Like look at Pmax. Well, only in one case do we think there is significant difference. The other is statistically not significant. There's a lot of noise. Look at that, 8 points, and we have all of them over a very large range. 6 points, the same thing. So very noisy data, not very convincing net effect. So is it because of bad data? It could be, or because of lots of variations among organisms? It's a good question. But the data obtained at the time, 2015, which only a few years ago, is not very convincing. Right? It's just a little bit noisy, and the noise could be variations among organisms, or it could be data that are just noise. Okay, but I think if I look at that and say, okay, I believe this, it seems to me that there's more of a positive than a negative effect. And I say that perhaps the effect of the high CO2, which is beneficial, is larger than the effect of the low pH, which should be detrimental. That's my conclusion. Not a very strong signal, but it's probably going that way. Not the effect on diatoms. Diatoms, which are of particular interest to me, you see are really close on average to no effect on it. All right, so not much of an effect on diatoms. Why? So I'm going back to work that was done by Brian Hopkinson, my professor at Georgia. And Brian did some very interesting studies. And this is the part where I'm going to lose some of my colleagues from from the poetry department. For a couple of the side, there's my colleagues in poetry. All right, so here's what. All right, so what Brian did is to use a tracer in which nothing is natural or main isotopes. Carbon is 13 instead of 12, and oxygen is 18 instead of 16. So it's a triply labeled CO2. It's not radioactive, it's a stable isotope. And this is a tracer, so it's carbon CO2 49. And we're going to follow, as a function of time, 3 masses, 49, 47, and 45. So 49 is T13, O18, O18. 47 is T13, O18, O16. 45 is T13, O16, O16. I can explain to you why we do it that way, but it's a very complicated experiment because you have lots of possible reactions, and you see some of them here. So the analysis of the data becomes fairly complicated. And so what Brian, this brilliant man, actually did was not only to do very nice experiments, and I'll show you the simplest possible experiment, where he used a mass spectrometer which has a membrane and you can follow the gases in real time, right? The CO2 can be measured in real time, you can measure the mass. So you could measure CO2 49, 47, and 45 in real time. Here there's nothing in the beaker except the water and the CO2. He adds a cell, things happen very quickly. And he can take those data and then say, okay, what does it mean? And analyze the data and make a whole bunch of experiments. I did some experiments also with some of the organisms that were genetically modified to have some enzymes that are overexpressed to be able to figure things out. So it's very complicated. But the point here is that student is following very carefully what happens to CO2 on the one hand, using isotopes, and 2, playing with the organism, the conditions of the experiments, and changing the organism itself to figure things out. And here is one result. It's a very simple diagram, which gives us the flux of the carbon into the cells and around the cell in units of 10 to the minus 17 moles per second per cell. And you see something very interesting, that a little bit of CO2 gets in and bicarbonate, but much of the carbon actually goes in circle, and a small fraction at every turn gets fixed by photosynthesis in organic carbon. So the thing is, we cycle the carbon. Essentially, it's forced to do that, and I'll show you what in a second, but it's a system in which, strangely enough, a lot of the carbon goes into the chloroplast of the cell, but only a small fraction, maybe a third here, become fixed into organic carbon. All right? And this is a final picture for this. The final idea that for a concentration of about 10 micromolar of CO2 in seawater, which is typical, we end up with a concentration at the site of rubisco. Rubisco is a high concentration, which is much, much higher. In this case, about 12 times higher. So you end up with a much higher concentration. So the problem that phytoplankton have had over billions of years, starting with very high CO2 in the water, decreasing over eons, they have solved by pumping the carbon inside, okay, and rather efficiently. And I'm quoting Brian's paper here, because I like those quotes. And the first thing which is really interesting is that the membranes around the cell are almost completely transparent for CO2. CO2 just goes in and out with almost same as in water itself. A little bit less, but not much. So CO2 can get in and out very easily, which means that you really have to play a game to keep it inside. The second part is this, which is very of interest to us right now. If you double the ambient CO2 from 10 to 20 micromolar, the energy expended for carbon fixation is estimated to be about 3 to 6%. And I think the lower number is much more likely, actually. And so, essentially, doubling CO2 would have very little effect on photosynthesis, okay? Despite the fact that CO2 is so important. So, the reasons we didn't see very much, I think, is very clear. The energy for concentrating the carbon is much smaller than the energy for photosynthesis, and CO2 and H plus leakage is minimized in those cells because of all those compartments. In particular, there's a compartment inside the chloroplast, which is not made of lipid bilayer, finished material, which is allows the high concentration not to leak out too fast. So it's a very interesting system in evolution to help the high concentration inside and pump it in a very, very efficient way. All right, then you go to other organisms. Those, as you've seen, if you go back a second here, I'm talking about organisms that have all kinds of subcompartments, right? So you can go to the evolution of that, but the point here is that you have a cell membrane, and another membrane of the chloroplast. In fact, there are 4 membranes of the chloroplast. There is a thing around the pyrenoid where the actual fixation takes place. So there are a lot of membranes that have to be crossed by the various solutes to fix carbon. So I'm going to take something simpler, which are cyanobacteria, because those are essentially without inside compartment, more or less, without organelles. And I'm going to use this organism called Trichodesmium. Trichodesmium is an interesting cyanobacterium. It forms those long rods where the cells attach to each other in length. It also forms this incredible things, puffs and tufts. And if you're a sailor and you go in the Sargasso Sea, and somewhere you go to see them by eye, they're large enough that you can see it's almost like hay on the water. Small, but you can see it. And the only time I've been to sea, I've seen them. The only time. I won't tell anybody. Okay. So the thing very interesting is that it's an extremely important organism in N2 fixation. As you well know, one of the problems of life is to take nitrogen from the air, N2, which is not usable by most organisms, and to the form which can be used. And this is one, and as you know, you plant legumes in order to fix nitrogen. Well, those are like the legumes of the sea, they fix nitrogen, which is an extremely important part in the ocean because nitrogen is probably the dominant limiting nutrient for growth of phytoplankton in the ocean. Here is a picture of a rather sensational bloom of those organisms, and you can see those rafts of those puffs and tufts at the surface, right? It's an incredible sight. Oh, by the way, I should go back. As far as I can tell, this is a dominant form. In most places, you don't have this magnificent thing that you can see. It's mostly this trichome, which is a series of cells in this rather thin form. All right. So I'm going to talk about work done by Dalin Shi. Dalin was a student here. He's a professor at Xiamen University in China. And he did a very nice thesis on this particular organism. He's continued doing that. And we'll talk about a recent paper that he's done in 2017 in Science. And Izeng Hong is actually his wife. I think she's the one who does all the experiments, actually. So that's an interesting thing. She's the first author of the paper. He's the last author of the paper. And I'm going to show you some results in a 2D plot. So I can do that here. pH, 2 different pH, 8.1 and 7.8. 2 different concentration of CO2 in atmosphere, 400 and 800. Normally, when they co-vary, 8.1 corresponds to 800, 7.8 corresponds to 400. Okay? They co-vary, as you may recall, from the beginning. So this first experiment shows what? When they both vary, CO2 is multiplied by 2, the pH goes up by 5.3 units, the growth rate goes down. We can actually measure this is an organism in which we see a strong effect of acidification. If you maintain the pH constant, as you can do here, and only vary the CO2, what you're going to do is actually increase the growth rate. If you increase CO2, they grow faster. Well, that's interesting, isn't it? The two together goes down, it goes faster. And I'll tell you that they did very nice work on proteomics, and I just can tell you right now that what you can see is that when you increase CO2, you end up with less rubisco, the big enzyme which has to fix CO2, there is less of it. And also the CCM, the one that concentrates the carbon, is also downregulated. So you economize on all the carbon fixation. Right? That's what you do. If you maintain the CO2 constant, and now you decrease the pH, the growth rate decreases, and according to the analysis of all the enzymes in the cells, you'll find many more enzymes doing the pumping of hydrogen ions. And you're going to find that there is ATP production is actually pushed up. There's more enzyme doing it, but in fact it produces less. So it's a rather interesting change. And finally, so if you do everything together, which I've shown you before, so this is the whole diagram, the point is that the effect of low pH is much larger. The negative effect is quite a bit larger than the positive effect of high pH. I won't show you all the rest of the data, but just a quick glimpse, which is interesting to us. One is some measurements of internal pH. It's a hard thing to do. You use it's not perfect measurements, but it's so dramatic that I think it is at least qualitatively true. And you see the pH under the different conditions are outside. The pH in the cytosol goes down dramatically between the starting point and the high CO2 low pH, and it varies a little bit under the other conditions. At the same time, we can look at the activity of nitrogen fixation. This is nitrogen fixation rates, and you'll find that it's a decrease from the control. And what you'll see is that there is in fact more enzyme and fixation, more nitrogenase. It's less efficient, it requires more energy. So part of the problem is that you end up with a low inside pH, and a lot of the enzymatic functions are affected. One of them is N2 fixation. And that's of course extremely important. So nitrogenase, by the way, is not quite as big as ribisco, it's also a very large enzyme. So there is a problem of low internal pH, which essentially makes a lot of problems for the cell. It's supposed to compensate in various ways. All right, so here's my triglycerin. Photosynthesis is actually improved by high CO2. High H plus, low pH is bad. That's what we expected to start with. At least one organism is doing what it's supposed to do. All right, we're happy with that. Now, there's a problem here, is that we do experiments in the lab with this, and I think it's the main form in the ocean. A lot of people who go to sea do experiments with those, because you can actually go and take a bucket and take a small pipette and collect them and take them away. So you can actually take individual organisms without all the mess around them. And so a lot of work has been done on those forms of the organism. In fact, okay, I'm sorry, I'm jumping ahead of myself. I've told you that already. And in fact, we had an undergraduate student here who went to Bermuda and started doing experiments. So I'm showing her data in which she actually looked at N2 fixations, okay, by colonies and with puffs and tufts as a function of pH. And you see that actually improves at low pH, just the opposite of what we have in the lab, okay, exactly the opposite. And she's not the only one to have found that. People work with those big assemblages to find always the opposite. And the reason for that is very simple. The problem with CO2 is that it has to get into the position of being pumped, right? It has to diffuse to the cell surface. If you get very large, diffusion becomes very inefficient, okay? I won't do the mathematics of that, but when you have large puffs and tufts, the diffusion of CO2 to the surface of the cell is very slow, and so you become very inefficient. So there was a guarantee here that very large organisms that need to fix CO2 are going to be really helped by high CO2. Right? The small ones don't get really as much. All right. Perfect timing. All right. Calcification. All right, more reactions. I'm sorry. Going back here, CO2 again goes into water. It reacts with carbonate ions. Remember, it's a main buffering for CO2, the acid and the base, making bicarbonate. And if you use CO3, you're going to affect the stability of calcium carbonate, which is calcite and aragonite. So that here, if you multiply CO2 by 2, you're going to divide the carbonate ion by 2, and you're going to make that precipitate less, or perhaps even dissolve. It's possible to make it dissolve in some conditions. All right, same stations as before. measurements of the carbonate ion, and you see it does decrease as predicted, performs exactly what's expected, and that's our low All right, so many marine organisms actually use calcium carbonate. Okay? And so I've put here one phytoplankton, the cochleosophorid, mussels here, theropods, which are small snails that swim in the ocean, and corals. All of those are of interest to people. All of them have been studied. And I'd say the people who are really worried about ocean acidification are the lovers of one or the other of this organism. Lovers because either they like to eat them or because they like to swim in them. Basically, that's been the public interest in ocean acidification comes entirely from this. All right? So, mention quickly two kinds of forms of calcium carbonate, aragonite and calcite. This one is more soluble, but it's less soluble. This is calcite, this is aragonite, it's very soluble. Those usually make both of them at the same time. I'm not going to go very long with cochleophophores. I've chosen this graph because it's not my own work, but basically what you see is that there is almost no effect. The first approximation people have published up and down and nothing. Cochleophophores do not seem to care very much about the change in carbonate ion concentration. This is very important for the French and the Belgians. A lot of those things. There's the Belgian over there, the mussels, the bull frit. Anyway, so those are extremely important things. Mussels, which are delicious, oysters, which are even more delicious. And then you have twice CO2. I'm not worried. I'm going to keep eating mussels and oysters. This is not going to happen. Right? The reason I started with the scale here, which is enormous, right? So effectively, in order to get an effect on this organism, you need to increase CO2 to values that you're not going to know in your lifetime. Or children, or grandchildren, or great-grandchildren. Corals. Again, I said corals are advent. I'm as part of a committee to look at ocean acidification. And the people who are the most interested are the people who dive in corals or work in corals. The coral lovers are an extraordinary bunch of people, very worried about all kinds of things because corals are actually dying around the world. Okay? And so acidification has been one of the pet peeve and an interest of coral lovers around many people in the world. The reefs are in trouble, you probably know that. Many of them are becoming white and dying. And they're very charismatic, as I just said. So I'm going to go on a few data, there are lots of data on corals, but I'm going to talk about some experiments done on Heron Island. So this is Australia, this is the Gold Coast here, this is Australia, and then you have Heron Island, which is the place where divers go. And I've been there once. It smells like bird poop. There's birds everywhere. But it is a paradise for divers. It's a great diver reef and so forth. Extraordinary diver reef. And here's some data of an in situ experiment. So let me stop a second here. Increase in CO2, you may have heard of the experiments in the Duke Forest called the FACE experiment. Free atmosphere carbon dioxide experiment, right? Where they actually take a piece of forest, things that put out CO2, and they pump it in the air depending on the wind, and you can have high CO2 for a long time. And an open experiment. This is called FOCE, F-O-C-E, Free Ocean Carbon Dioxide Experiment, right? You get the idea, which essentially uses a very large enclosure on the Great Barrier Reef to do the experiment. So the reason I chose those data is because they seem to me more real, perhaps, than taking a piece of coral out and putting it in the beaker. You have all the effects of all the organisms that are there. So it's an in situ experiment. And here we see what? Now, this was before they started the experiment in the month of June. And this is the pH outside, 825 or so. And this is measured inside the organism in the calcifying compartment. So I really like that because it tells us something about how they can calcify, right? So it's inside this particular compartment. And you see, first of all, it's a high pH, which makes sense. If you precipitate calcium carbonate, you want a high pH, right? And you can see that those values are here. The treatment and the control are the same because the treatment is the control here. Now, in August, when the treatment is so young, you have a clear decrease, okay, of a clear increase, if you look at the word, okay? What's happening to me? Clear decrease in the pH in the treatment, yes, okay? And you see almost no effect inside the organism. In other words, the organism is able to buffer the calcifying pH almost perfectly. Those corals have a way to pump a number of ions, including protons, in and out in such a way as to control the calcification process. Same thing in September. In November, well, they had a problem. They had a storm, pretty much lost the experiment, and so that's what, when you do field work, it sometimes happens that it doesn't work. Right?
What is treatment here?
Treatment, okay, so treatment is simply a decrease in the seawater pH. You actually acidify the seawater, and you see what happens to the organism, in particular in this case to the pH at the point of calcification. Okay? By the way, this particular organism is a major reef builder in the Great Barrier Reef. It's an important organism. So the point is that coral emitted calcifying water out of seawater. I took another paper to look at something else, which is when do you get an actual decrease in calcification? And this is work of people who work at Monaco. Monaco, you may not know this, is a small country with a lot of money because they are gambling, and they have a very important research facility for oceanography, a very old one. Prince Albert, whatever the first, was the first one to do that. So they have a long tradition of studies of corals in particular. Anyway, a bunch of papers published by those people in Monaco, and this one shows that they had to go down to 7.2 pH to start seeing the beginning of the loss of the shells of the corals. Okay? All right. So my reading of literature, which is complicated, is that acidification is probably not a major cause of the coral loss around the world. Okay? Coral loss is a real thing, it's happening, it's bleaching everywhere. I think acidification is at best, at worst, a minor player in this phenomenon. Now, this being said, some corals are more sensitive. A recent paper that says that a different family of corals may not be as well buffered in terms of the internal pH, some are more sensitive. But I think it is really warming, particularly, pollution in some places that's responsible for the loss of corals. So, I agree, we can argue about this, but in my sense, it's not acidification. It's really other human causes, but not acidification, principle. Other knowledgeable effects. Quick conclusions. Okay. Acidification is modest effect. Increased CO2 is beneficial for some photosynthetic organisms. And the internal pH homeostasis is very small cost for most organisms. The ecosystem is resilient, and I put four reasons that are important. The first one is that there is a rapid turnover of primary producers. The fact that phytoplankton, which divides every day, it's not like a tree which is not going to go to walk north. You know, you can't do that. Trees cannot take their roots out and go anywhere. Phytoplankton is a problem. Adaptation of unicellular organisms, which are the basis of all the ecosystems, can adapt much faster than multicellular organisms. The fluid medium, the dirt doesn't change very much. If it's fluid medium, it can mix the organism all the time. And finally, there's an interesting thing about the prokaryotes, that they can exchange genes. There's a lot of very nice recent work showing the exchange of genes in the Prochorococcus species or Vibrios, in which essentially you look at one particular isolated, there's a certain number of genes, and it's further away, it's a different set, and they can exchange with them rapidly, which means that's not one organism, it's a, what do you have a name for it, and I can't remember.
Collective.
What's that? It doesn't matter. The ensemble of all the genes of the same organism around the ocean. Okay? So, old age. Sorry. All right. And it seems to me an interesting question, since I've from EEB friends in the room here, is a contrast between this marine ecosystem and terrestrial ecosystem, which also have to respond to global change, but I think have a different set of constraints, are very different, and perhaps in fact more dramatically affected as a result. Thank you.